Every month, the National Epidemiological Tracking System for Stunting absorbs millions of individual child measurements. Yet, district health offices consistently face a paradox. They are data-rich, but information-poor. Massive national databases compile these measurements into aggregate monthly tables. These tables show broad historical trends, but they fail to tell a clinician at a local health post exactly which child needs an immediate, specific medical intervention today. To solve this problem, the Malong District Health Office deployed the SIGMA ecosystem. SIGMA stands for System Information Gizi Integrasi AI, a localized, interconnected digital platform built to process public health data. The platform enforces a strict operational framework known as Tindik. This is an acronym for a four-step methodology: early detection, intervention, accompaniment, and evaluation of stunted children. Standard digital reporting and data dashboards typically function as static mirrors of existing databases. SIGMA is a deterministic data science pipeline. The architecture mathematically cleans raw input data, tracks clinical nutritional interventions longitudinally, and utilizes rigidly constrained artificial intelligence to generate localized health policy. To understand how this works, we have to deconstruct the architecture layer by layer, tracing the data flow from the initial measurement at a village health post all the way up to executive policy generation. Reducing stunting depends on an engineered architecture that forces massive, passive datasets to become hyperlocal, actionable intelligence. All public health databases share a primary vulnerability: measurement error at the village level. If a health worker logs an incorrect weight or height, it corrupts the dataset and skews all downstream policy decisions. The first architectural layer designed to mitigate this is the SIGMA calculator. This module performs bulk validation on incoming data using the strict WHO Z-score LMS method. The LMS method, lambda, mu, sigma, is a statistical technique used to calculate Z-scores for skewed growth distributions, like weight and height, by accounting for skewness, the median, and the coefficient of variation. Beyond standard validation, the system employs a predictive feature to calculate probable stunting. This chart shows how the system utilizes a growth age equivalent approach. Growth age equivalent is a metric comparing a child's current physical measurements to the median age at which a healthy child typically achieves those same measurements. Here, the child's current data sits above the official stunting threshold, but the system calculates that their growth trajectory projects downward, isolating them in a high-risk zone before they officially register as stunted. This shifts the operational focus. Instead of solely flagging children who are already stunted, health workers can identify and intervene in high-risk trajectories weeks or months in advance. By mathematically validating inputs and projecting future growth trajectories, the calculator executes the first pillar of the Tindik framework: early detection. Once the localized input is validated, the data flows upward into the central warehouse, the SIGMA RCS, or Reporting and Command System dashboard. The RCS actively mirrors the national CGZ Cascade database, but it subjects the data to advanced scientific analyses that the national system does not perform natively. The engine parses this mirrored data using WHO team guidelines and the CFAF. CFAF stands for the Composite Index of Anthropometric Failure, a metric that identifies the proportion of children experiencing multiple forms of malnutrition simultaneously, such as being both stunted and wasted. This table shows the output of the most powerful analytical tool within the RCS, Structural Equation Modeling, or SEM. SEM is a multivariate statistical method that analyzes simultaneous relationships between dozens of variables to identify exact causation. Instead of guessing what causes local stunting, the SEM mathematically isolates it. Here, the system proves a direct correlation between the percentage of pregnant women with anemia and the overarching stunting rate, verifying the relationship with a significant p-value of 0.010. A p-value is a statistical measurement used to validate a hypothesis. A value of 0.010 indicates a 99% probability that the result is not due to chance. It simultaneously calculates the impact of protective factors. In the same dataset, the model isolates good complementary feeding, the introduction of solid foods alongside breast milk, as a significant variable, calculating its exact mathematical coefficient against the stunting prevalence. Isolating these exact mathematical coefficients is crucial for resource allocation. It prevents local governments from exhausting their budgets on broad, generalized health campaigns that do not address the specific statistical drivers in their district. The RCS transforms a static repository of measurements into an evidence-based policymaking engine, proving precisely which localized factors require intervention. Identifying a problem and calculating its cause yields no physical result if the subsequent clinical intervention is not rigorously monitored. This introduces the third architectural layer, the PKMK module. PKMK refers to specialized medical food formulations prescribed by physicians for the dietary management of children with clinical malnutrition. This timeline shows how Sigma differs from traditional tracking. While standard systems tally the aggregate monthly headcount of supplies distributed, the PKMK module enforces longitudinal compliance tracking. It maps specific doses given to a patient over time and overlays that data to track the upward trend in the cohort's average Z-score. The module actively monitors cohorts of red flag toddlers, those in critical condition, who are receiving these highly specific, heavily subsidized medical food formulations. If a specific child's weight fails to increase despite receiving the prescribed intervention, the system automatically triggers an alert to local health workers to evaluate for underlying clinical issues. The PKMK module closes the feedback loop. It ties targeted government nutritional investments directly to measurable, real-time physical outcomes. With the RCS and PKMK modules generating massive amounts of multivariable insights, a scaling problem emerges. How do local policymakers quickly parse this data to make immediate decisions? To bridge this gap, the ecosystem integrates the Sigma Advisor, an artificial intelligence assistant powered by Google Cloud Vertex AI. Applying large language models to clinical data carries a catastrophic risk. AI models hallucinate, and generating fabricated data in a public health context can result in dangerous policy directives. This diagram shows the explicit architectural workaround Sigma uses to neutralize this risk. The system operates without a vector database, explicitly preventing the AI from independently searching for its own data. Instead, a dedicated Node.js server acts as an aggregation engine, pulling raw, relational data directly from the Supabase warehouse. The server then executes a mathematical compression phase. It reduces thousands of rows of operational data into strict percentages and absolute counts, structuring them into a dense, compressed format. This compressed context is injected into the AI alongside a hard prompt instruction stating "never invent data." Furthermore, the API call is executed with the temperature setting locked at 0.3. Temperature is a parameter that controls the randomness of an AI's output. Keeping it near 0 forces the model to generate a strictly deterministic, non-creative response. By stripping the AI of its capability to invent information, the pipeline leverages only its advanced reasoning and summarization skills to generate mathematically sound, locally accurate policy directives. The final barrier to systemic public health reform is interdepartmental data silos, where different government branches operate using conflicting or outdated statistics. Sigma resolves this through its final architectural component, the API gateway. This terminal visualizes a REST API payload schema routing to an external dashboard. A REST API, Representational State Transfer Application Programming Interface, is a standardized architectural style that allows different software applications to communicate and share data over the internet using specific requests. The gateway provides third-party government systems direct access to Sigma's verified metrics. To protect the integrity of the database, the API enforces strict security protocols. It is entirely read-only, restricts access via unique API key authentication, and employs daily rate limiting to prevent system overload. An API key is a unique identifier used to authenticate a calling program to an API, ensuring only authorized government systems can access the data. The API gateway elevates Sigma from an isolated tool used only by the health department into a foundational data layer that drives coordinated government convergence. When observing the macro impact in Malong District, the complete architecture of the system becomes clear. Complex epidemiological challenges like stunting cannot be solved simply by acquiring more data. Eradicating the problem requires building an architecture that forces that massive volume of data to be validated, analyzed, and translated into immediate action. The Sigma flow is interconnected by design. Rigid input validation at the calculator feeds directly into the multivariate analysis of the RCS. Those statistical findings trigger physical interventions tracked by the PKMK module, and the results are distributed by a deterministic AI. This continuous pipeline shifts local governance. It moves the district away from reactive data gathering and equips them with the capability for proactive, evidence-based policymaking. The framework deployed here serves as a scalable, open-source blueprint for national healthcare transformation. By dismantling departmental silos and mathematically enforcing clinical tracking, public health surveillance transitions from a static historical record into a dynamic, predictive engine capable of securing the next generation.